Okay, so the intersection of two planes, we have three major cases again. Our first case is when plane 1 intersects plane 2. They form a line, okay? And that's very important because before we were looking for just coordinates when lines crossed each other. When a plane crosses, we're going to be looking for the equation of a line, whether it's in vector form, okay? So r equals vector r naught plus t direction of vector A, or parametric, x is x naught plus ta, or even Cartesian, ax plus by plus cz plus d equals r0, okay? So we could be looking for any of these in terms of when planes intersect each other. Case 2 is when we have two parallel planes. There will be no solution to this, okay? This would be considered our one solution, or our one equation of a line. This case 2 will be no solutions. And case 3 will give us an infinite number of solutions where we have coincident planes. It's actually the exact same plane is what we are talking about, okay? So I'm going to jump into the first example, and they've given us the equation of two planes here. Let's jump ahead. I'll put that back up again in a second. So plane number 1, they've given us x minus y plus z is equal to 4. And plane number 2, they've given us the equation of x minus y plus z equals 5. Okay. Now, if you look back to the other page, our goal is actually going to be to disprove cases 2 and 3 first. We're always going to look to get rid of coincident and parallel lines first because they're the easiest to find. And if it turns out they are parallel, great. If we're able to disprove them quickly, then we know we're just working on number 1. So, what I need to disprove here? Well, if you take a look at these two, I'm going to get the normal because right now we're in Cartesian form, and if you guys remember, the normal is ax plus by cz plus d equals 0. The normal of plane 1, or any of the normals, will refer to ABC, those points. So normal of plane 1, in this case, we'll just call this normal, the equation of a normal. The normal of 1 is at point 1, negative 1, and 1. And the normal of 2 is 1, negative 1, and 1. Well, if both the normals have the same direction to them, or they're the same numbers, we know we have what? Parallel. We know the planes are parallel for sure. We just got to figure out if they're coincident. Okay? And this is actually quite easy to do because when I actually set these two equal to 0, plane 1 and plane 2, so we already know they're parallel, so it could be either case 2 or 3 right now. Plane 1, when in Cartesian form, is x minus y plus z minus 4 equals 0. And plane 2, x minus y plus z minus 5 equals 0. Well, our d values are different, okay? And there's no scalar. I'm not going to be able to multiply plane number 1 by some number to get plane number 2. So because it's not a scalar multiple of the other, we know they're not coincident lines. These are planes. These are parallel planes. So this is case 2. We have plane 1 and plane 2, and they're parallel to each other. They will not intersect each other. Okay? And the way you can show that algebraically is by some elimination. Let's say I decide to multiply the very first equation, or plane 1. I'm going to multiply by negative 1. So I now have negative x plus y minus z plus 4 equals 0. Okay, and I could also just put that number on the other side, which I'm going to do. Let's make it equals negative 4. And we're going to add it to the other equation, x minus y plus z equals 5. When we add those together, 0x plus 0y plus 0z is equal to 1. There is no value of x, y, or z that when I multiply them by 0 will get me 1. Okay? So in other words, there's no solution to this. And we know these are parallel lines. Or planes, parallel planes.